Fermaflavones are natural isoflavones that can be recovered as co-products from soy-based industrial fermentations. Isoflavones are used in many markets. The nutraceutical market includes food and beverages. Also, isoflavones are used in human health supplements and cosmeceutical ingredients as UV-blocking agents. They are also sold in pure form as specialty chemicals. The isoflavone structures as they occur in soybeans are shown here. Genistein and daidzein are found in about equal proportions in the soybean at a concentration of about 0.25% by weight. The isoflavones in soybeans are in the glucoside form, and the two structures differ only by one hydroxyl group. The desired form of the isoflavones are the aglycans genistein and daidzein. So at some point in the process of recovering isoflavones from soybeans, the glucose groups must be removed from the structure. A commercial fermentation tank can produce about 1,000 kilograms of erythromycin and about 5 kilograms of pure isoflavones. However, because isoflavones have much higher value than erythromycin, the co-product recovery has the potential to double the revenues from an erythromycin process. Isoflavone extracts, that are partially purified, are easier to produce and are sold at comparably lower prices. A typical erythromycin fermentation goes for 5 days. During this time the isoflavone glucosides disappear and the erythromycin accumulates. Erythromycin is harvested by extraction into the solvent layer, then back extracted into acidified water. What happens to isoflavone glucosides during the erythromycin fermentation? Isoflavones are rapidly metabolized during the erythromycin fermentation. The isoflavones appear to be degraded during the fermentation. For our purposes we needed the biotransformation to be stopped at step 2, so that the aglycans would remain intact in the broth at the end of the fermentation. With a block at step 2, the aglycans would persist in the broth until the end of the fermentation on day 5, at which point they would be extracted with the erythromycin by the solvent. Next the aglycans would be separated from the erythromycin during the next extraction with acidified water. The two products would then be recovered from these two different recovery streams. The problem was that isoflavone metabolism could not be stopped at step 1 or step 2. The solution to the problem was to let the natural biotransformation process proceed, and at the end of the fermentation, convert the biotransformation products back to the desired compounds, with a simple and efficient treatment process. Analysis of fermentation broth samples from a fermenter showed that biotransformation products from any stage of the process could be converted back to genistein or daidzein by a simple treatment process. The same amount of isoflavones could be seen at the end of the fermentation as could be seen at the beginning. Other fermentations were also investigated. In most cases the isoflavones recovery could be improved by using a process similar to what was developed for the erythromycin fermentation. The final co-product recovery process would look like this. The biotransformation products remain in the extracted broth after erythromycin is removed. They are then removed by a second extraction process using a more polar solvent. The twice extracted broth is shipped out from the plant to be used as an animal feed supplement. The acid and heat treatment efficiently converts the biotransformation products back to the isoflavone aglycans. The aglycans can then be sold as a partially purified extract, or further purified into genistein and daidzein. The advantages of fermaflavone production are, first, a significant increase in revenue stream is obtained. Second, an economical and simple process is used, requiring no modification of the erythromycin manufacturing process or the erythromycin producing organism. And finally, multiple markets are available for fermaflavones depending on the degree of product purity. The technical problems associated with fermaflavone co-product recovery have now been solved. The process is now ready for scale-up and commercialization. Contact Fermalogic now. Visit our website at www.fermalogic.com. This work was made possible through generous grants from the National Cancer Institute and the Small Business Innovation Research Program. Fermalogic personnel that contributed to this project are Andrew Reeves, Igor Burkin, William Cernota, Ramya Seshadri, Melissa Gonzalez, Benjamin Leach, Roy Wesley, and Mark Weber.